thing that we noticed about lots of galaxies is that, like the Milky Way, they are spiral galaxies. And so the issue of understanding how spiral galaxies come to be spiral is an old and interesting one, and I want to explain why it's a problem first. So one could imagine that for some reason stars form in a pattern like the one at right, and therefore you have spirals. That is not the solution to how spirals form. We understand that because remember that within the region where the sun is, rotational velocity was roughly constant. If rotational velocity is constant, then periods of rotation are not constant. Stars on the interior moving at the same speeds as stars on the exterior, the interior stars will orbit with much shorter periods because their orbits are shorter. What this means is that if you imagine creating a galaxy with this pattern and then letting the stars rotate, and remember that the sun has gone through about 25 orbits of the Milky Way, so this is not some theoretical construct. What happens is the inner stars orbit faster than the outer stars, and the arms get all wound up and eventually will dissolve. After a few rotations, you have no spiral left. You cannot construct a spiral galaxy as something you're actually going to find by having a spiral being a place where stars are. In general, since the sun takes 230 million years to circumnavigate the galaxy, and remember that spiral arms are the position where we found O and B, hot O and B type stars. And since O and B type stars don't live 230 billion years, by the time the spiral arms complete an orbit out where the sun is, it's a whole new generation of stars. Many new generations of stars have come up. And yet the spiral arms must be stable, otherwise we wouldn't see so many spiral configurations in galaxies. So what is it that allows spiral arms to survive? Well, the model that was proposed by Lin and Xu in the 1960s is called the density wave model. And the idea is that spiral arms are not material objects. They are propagating density waves propagating through the disk. The wave propagates, as you recall, with a completely velocity that is the wave velocity. It's completely independent of the motion of the actual objects in the disk. When we had a wave going down a string, the string wasn't moving at all, and the wave propagated down the string. So these waves propagate through the disk with their own velocity, and what this implies is these are like sound waves. There are regions where the density in the disk increases by, say, 10 or 20%. And how do you generate such a situation? Well, there's this nice image here on the right. What we have here is a bunch of elliptical or oval orbits, and you can imagine that in each of these orbits there are a whole bunch of stars, each following that orbit at various places along the orbit. And these ellipses or ovals are tilted slightly with larger and larger radius. And you see that this creates, this twisting creates regions in the galaxy where the orbits are close together. This is a region of enhanced density. If you imagine that each oval is equally populated along its length by stars, then in the regions where the ovals are close together, there will be an increased population of stars and gas and whatever it is that's orbiting along these orbits. And the fact that the stars on the inner ellipse orbit faster than the stars on the outer ellipse has nothing to do with it. If these orbits were actually steady, then this pattern would not shift at all. It would stay completely constant because every star, as it hit the part where where the orbits are bunched up, would experience higher density. Now, in practice, this is not a stable situation. Stars orbiting along these orbits, anything but a collection of circular orbits, leads to gravitational interaction, and so these orbits will in fact precess if you put stars in these elliptical orbits, and that precession will lead to the different tilts of the different ellipses changing at different rates. If you have a resonance that between the precession period and the orbital period, then you can have a situation where what the precession sets up is not the complete destruction of this spiral, but rather a slow rotation of the spiral over time. And then what you have is a situation in the disk where you start with a population of stars and dust and gas and whatever, But there are regions where the density is higher. Now, stars as they orbit enter this region and then they exit it. Clouds of gas enter this region and exit it. When a cloud of gas encounters this region of higher density, that's higher pressure, the cloud of gas is compressed. Some clouds may become critical in the gene sense. They will then begin to collapse, and by the time those clouds are exiting the spiral, at the leading edge of the spiral, you will find brand new ONB stars that have formed while the cloud was collapsing inside the spiral. Remember, the entire lifetime of an OB star is maybe 10, 20 million years. Orbital periods near where the sun is 200 million years. So the stellar stars that were formed by entry into the region of increased density will live out their lives, the OB stars, not far from that region. Now, even if all stars are formed in the spiral arms, stars that live longer will have time to orbit away. And so you'd expect the red stars to be far more uniformly scattered, but the regions of star formation will be at the region of this density wave. And this, we think, is how spirals survive. And so simulation of what this looks like is, here is this density wave set up, and as the stars orbit, the arms orbit with an angular velocity that has nothing to do with the angular velocity with which the stars, either inside or on the outside of the galaxy, orbit. And in the simulation, we see that the arms are stable, and we've also decorated them with blue stars and red H2 regions to make it look like this beautiful example on the right, M81, a classic, what is called grand design spiral with very coherent spiral arms populated by lots of blue stars and lots of H1 regions, H2 regions, ionized hydrogen regions, where hydrogen has been ionized by the ultraviolet radiation from these new hot stars. And so the density wave model is a very successful model for describing these. It's a little more difficult when you come to describe what is called a flocculent spiral, like NGC 4414 over here, where the spiral structure is less coherent. And the model that may play a part in describing the spiral structure, which nonetheless is present here, may be a model called SSPSF, for stochastic self-propagating star formation, proposed by Müller and Arnett in 1976. And the idea is that star formation begins in a roughly uniform disk randomly. At some point, stars begin to form. Some cloud collapses. The first stars to form as a cloud collapses, of course, are the biggest ones because they form faster. And so you get ONB stars. The ONB stars live their life and end their main sequence existence before many of the smaller stars have even passed the protostar stage. And then the supernova explosions from these stars create shock waves that propagate through the cloud and basically blow it apart, inhibiting the growth of further stars. So whatever young stars that passed the protostar stage are going to get onto the main sequence and stay on the main sequence, because stars are not blown away by the shock wave. But the gas and dust is going to be blown apart, and therefore star formation ceases. So if you start with star formation in one place, it basically blows itself apart, like a forest fire burns itself out. But like a forest fire, the same shock wave can be like a spark, because farther out, when it is no longer as concentrated as when it blew this cloud to smithereens, farther out after it is diluted a bit, this shock wave can be precisely the trigger. Remember, we needed a trigger to cause a cloud to suddenly become critical. It could be the density wave, it could be the shock wave from a supernova, causing a nearby cloud to now become critical and start collapsing. And so like a forest fire, this process of star formation will propagate in all directions through the disk. When it propagates through the disk, the differential rotation will wind whatever shape these regions of propagating star formation initially had. The differential rotation, the fact that stars on the interior orbit faster, will wind it into this spirally shape. And this might be the model that describes flocculent spirals, and maybe there is some combination of the two that is in action at all times, because we see that both of them seem to be reasonable mechanisms. But the question of spiral arms is at least intriguing.